Alright, now we're going into graphing logarithmic functions, and we're still focusing on logarithms here. Prereqs for doing this are heavy prereqs actually. They're very required. Exponential functions, you have to know pretty much everything about exponential functions at this point, which means that you need to know everything about exponential functions. Specifically, you need to know how to graph them. And so far, the only way I've really taught how to graph them is by plotting points and also to recognize some properties. But anyhow, you also should know about logarithmic functions, which is the previous lecture. If you don't know about logarithmic functions, please go watch the previous lecture. You should know about logarithms as well, obviously. Inverse functions, that is a lecture I have done recently, so please go back through. And finally, functions themselves. You should know about functions, domain and range, and all that fun stuff. And just recall that the logarithm really is defined in terms of an exponential function. So b to the y is equal to some number x is the same thing as saying log base b of x is equal to y. But this is important for our building of some concepts for logarithmic functions. In fact, let's go ahead and tackle that theorem, one of those theorems right now. The domain of the logarithmic function f of x equals log base b of x, where b is again positive but just not 1. That domain is 0 to infinity. And the reason why, and I mentioned this in a previous lecture, but I never really justified it, so this is where the justification occurs. The reason why is, well, consider what the domain represents. The domain represents all the inputs that I can plug in for x. So it's all the values that x can be. Now, I wrote this up above for a specific reason. Instead of calling it f of x, I'm going to call it y here just to illustrate something. And so if y is equal to log base b of x, then x must equal b to the y power. Okay. And remember, b is positive, and it's not equal to 1. So let's talk about if b is positive and not equal to 1, what are the possible values that x can take? So for now, I'm asking you to ignore this down here. We're just going to prove that it's true, kind of verbally. So y equals log base b of x is the exact same thing as saying b to the y is equal to x, and I'm saying if b is positive, then what can the values of x be? Well, all they can be is positive. So this must be greater than 0. Has to be greater than 0. It can't be 0 at all because you take any positive base and raise it to any power you want, and you're not going to get 0. You're always going to get some positive number. That's why x, because these are the same x's in both of these equations here, the same x's, that's why x has to be positive. So I'm going to now do that big reveal down here, even though you could see it before. But that's why our domain is at least positive. Now the question is, why does it go on to infinity? And we'll investigate that when we begin to graph the logarithm. But suffice it to say that if you take a look at this function right here, and remember, b is positive, y could be anything I want, actually. So I could plug in any value for y here, negative billion, positive 3,000, whatever I want. If I plug in, let's say that b, the base, is like 5. In fact, let me bring up another page for that. Let's suppose that the base is 5. So we're talking x equals 5 to the y, which is equivalent to saying y is equal to log base 5 of x. They're equivalent statements. Plug in any value you want for y. If you plug in like a trillion, or well, something that I could write quickly, let's just say 3,000. How large is that number? That's pretty. 5 to the 3,000th power is huge. So this means that x can be insanely huge. Okay, and actually, because I get to choose a value for y, y could be huge as well. Or I can let y be very small, like a 0.3, right? If I do y equals 0.3, then x is not so big. Okay. I can let y be negative. If I do that, that's just going to be the same as 1 over 5 to the 100th power, which is a very small number, but still positive. Okay, so still greater than 0. So what I see are two things occurring here. The x values can range from things that are almost 0 all the way up to huge numbers, and I see that my y values can be negative numbers, positive numbers, huge positive numbers. So this means that, going back to this form right here, that my inputs can be any type of number that's positive, and my outputs here can be any number I want. So I wrote that down here as a theorem. The range, which is a set of outputs for this function, for the logarithmic function, can take on any value. And like I said in this example here, depending on what I want to plug in for the y values to this exponential function, which are these same y values. That's why I'm saying I can plug in anything. Since I can plug in anything for y over here, that means this y can be anything. Okay. But no matter what I plug in for y, x is always positive, but I can make it as huge as I want, and I can get all the way down to, but not actually touching 0. So this, I can get all the way down to 0 but not touch it, and go all the way up to infinity if I wanted to. Now let's recall a fact from the inverse lecture that I gave not too long ago. The graph of a function and its inverse are just reflections about the line y equals x. So for example, if this was the graph of f, the one in blue, and the black line here is the line y equals x, then if I wanted to quickly graph the inverse function, I would essentially think of this black line as being a mirror and try, maybe not effectively, but try my best to graph this mirrored reflection here. And probably one of the best ways to do that is just to take some sample points along here and swap their x and y values. That really is, I think, the best way to do it. So let's just pretend that this x value is a 1 and the y value is a -1, and this x value right here is, let's pretend, 1.5, and the y value is a -2. I don't know why I put a parenthesis there. And this last one might be an x value of 2, and this might be a -4. I'm just making things up, okay? Same thing for these points back here, that these points might be, again, I'll just say it's like a -1, 1, and this is like a -1.5, 2, and this might be a -2, 4, or something like that. Now, if I want to graph the inverse, I will just flip the roles that these points take. In other words, instead of graphing 2, -4, I'll graph -4, 2. So in other words, go back 4 and up 2. So let's just pretend it's, oh, well, it can't be right there, actually. It has to be up here. That's -4, 2, let's pretend. And then I want to graph -2, 1.5, which was likely right there, and then -1, +1, which is right there. So I get something that looks like this. And actually, now that I see that, I can probably just say it does something like this. I kind of see the pattern, how it works. That's how you graph an inverse. You plot points, and you just you plot points for one function, and then you swap the roles of the x and y values and plot those out to get the inverse. Of course, that's a quick and dirty way to do it. There are other ways you can do it, but this is really the quick and dirty way to get around to doing it. So for example, let's say we were asked to graph f of x equals log base 4 of x. Now, I do not know, well, okay, I do know, but you don't know at this point what the graph of a logarithm looks like. but you should know what the graph of an exponential function looks like. So if we know that the function f is equal to log base 4 of x, I'm going to first graph its inverse because I know how to graph the inverse. The inverse function here actually is 4 to the x power. That is just an exponential function with base 4. And remember, if you have a base that's greater than 1 on an exponential function, it means that it's an increasing function. Every step, remember I mentioned with exponential functions that they have the base multiplier property, which means in this case that every time I increase the x value by 1, the output gets multiplied by 4. So let's go ahead and graph this one. When x is 0, we have 4 to the 0th or 1. I'll just plot that there. When x is 1, we get an output of 4. When x is 2, we get an output that's 4 times higher than that. So every time, like I said, that you take a step, the output gets multiplied by 4. So I'm going to go ahead and plot that one. And in fact, I'm just creating a table here so that it may look more logical to you as we're going through. So I've plotted 3 points, but 3 points are not enough to plot an exponential function. We should probably go back a few in the negative direction. So we'll go ahead and put the negative values in here as well. That's going to be a -1. When you plug a -1 in for x, you get a 1/4 out. If you plug in a -2, you get a 1 over 16. Okay. And those are really hard to actually plot on here because maybe 1/4 is not so bad. It's probably right about there. 1/16 is even closer to the x-axis. So, and I purposefully chose this scale like this just to kind of really demonstrate how exponential functions work, that they just blow up in value. But let me go ahead and connect these with maybe a different color. Now, a couple things, I know I didn't do it in a different color, but I already started drawing it out in black there. A couple things I want you to note here. This is not the graph of the logarithm. This is the graph of the inverse of the logarithm, which is the exponential function. Another thing, this graph, as it goes negative in the x direction, it gets really close to the x-axis. It never touches it, and it's very difficult to draw on a screen like this that it never will touch the x-axis, but it actually never does touch it, and it goes on forever. Okay, so if you can imagine it keeping going to the left, it does. And finally, what we need to do to graph the logarithm is just swap these x and y values. And if you're just kind of eyeballing this, some instructors are okay with you just drawing a diagonal line here and kind of throwing the mirror image on. So I just go ahead and graph really quickly the line y equals x. I'll just demonstrate kind of what some instructors might be okay with. If you imagine this being a mirror and you want to graph the mirror image, it would look something like this. Oh god, it doesn't look like that at all. It looks something like this. God, doesn't it look about the same? As bad? Anyway, it looks something like that. But I'm going to be a little more accurate than this. I'm going to go ahead and plot the points. Okay, but if you can see, these kind of do look like mirror images about the line y equals x. But I think that's too messy. I probably would not accept that. So over here, I'll do a table for the inverse, or I mean for the regular function f. And what I'm going to do to build this table is just, well, flip the roles of x and outputs here. So in other words, this will be 1, 0, this will be 4, 1, this will be 16, 2, this will be 1/4, comma, -1, and finally this will be 1/16, comma, -2. That's what's nice about building a table to do this. Alright, when x is 1, the output is 0, so it's right there, which is a mirror image of 1, comma, or 0, comma 1. When x is 4, so 2, 3, 4, the output's 1. When x is 16, the output is 2. Something like that, 16, comma 2. All right, and when the x is 1/4, the y value is -1. And when x is 1/16, which is just really close to the y-axis, the x value, or the y value is -2. So maybe I'll even denote that 1/16, comma, -2. And then you connect these dots. And that right there should be, hopefully, the graph of f of x. And remember, this one up here is a graph of f inverse of x. Okay. That's generally how you graph a logarithm the first few times. After you've graphed logarithms a few times, though, you know they all kind of look like that red curve there. They have a vertical asymptote at the y-axis. And all that basically means, a vertical asymptote at the y-axis means that essentially the graph, the red curve here, the graph of log base 4 of x, cannot touch or cross the y-axis. Okay? If I say I have a vertical asymptote at the y-axis, it means the graph can't touch the y-axis. You could have, by the way, there are functions with vertical asymptotes elsewhere, like at x equals 2 and x equals 5, stuff like that. And we'll see those in a future topic, rational functions. But for now, this should be your first introduction kind of to vertical asymptotes. They're kind of neat once you get used to them. But luckily, this is all we need them for here. It's just to say that, well, the graph's getting really close to the y-axis, but it's never going to touch it. Okay? And then they all kind of have the same behavior where they rise very slowly, actually. Logarithms, their outputs increase continually. It'll grow big. It'll grow very large. In fact, it'll grow infinitely large, but at a very slow rate. So let's go ahead and see what else we can kind of say about graphs of logarithms. Now let's recall properties of exponential graphs first. So given a function a times b to the x, we know it's an increasing exponential function if b was greater than 1, and we know it's decreasing if the base is between 0 and 1. Now, this is the only property that doesn't change when we're talking about graphs of logarithms. Logarithmic graphs also are increasing if the base is greater than 1, and they're also decreasing if the base is, well, between 1 and 0. So there we go. That's this second property right here for the property of the graph of properties of the graph of the logarithmic function. It's increasing if the base is greater than 1, decreasing if the base is between 1 and 0. The second property, and this is where we start talking about the inverse behavior of the two functions. This core bracket here, you pay attention to what happens, the difference between this for the exponential graph and this for the logarithmic graph. Remember, the roles of x and y swap when you get to logarithms. So for exponentials, the y-intercept is at 0, a. The domain is all real numbers. The range starts at 0, goes to infinity, and we have a horizontal asymptote along y equals 0. So all that stuff, you know, we have a y-intercept, our domain's all real, range is all positives, and we have a horizontal asymptote. All that stuff swaps for the logarithm. So that group that we had in the exponential functions, those dealing with exponential functions, all those kind of properties or traits swap x and y values here. In other words, in this case with a logarithmic function, instead of having a horizontal asymptote, we have a vertical asymptote. And instead of it being at y equals 0, because it's a vertical line, it's x equals 0. Recall that all vertical lines have equations x equals solid number, some constant. Again, the exponential function has a y-intercept, so therefore the logarithmic function must have an x-intercept. And in this case, the x-intercept is always going to be 1, 0. Okay, I say always, but I should kind of qualify that by saying as long as this has no shifts to the function. And all these functions, both these functions I should say, exponentials and logarithms, can be manipulated with shifts, translations, and reflections later on. And I might just actually do a lecture or another video for that as well. Again, exponential functions, they have a domain being all real numbers and a range being just positive real numbers, whereas logarithmic functions, that swaps, right? The domain is only positives, the range is all real. So let's use these to actually graph a logarithm without graphing the exponential function. So in this example right here, I'm asking us to graph the function 3 times the log base 1/2 of x. Now what I'm really going to do is just graph log base 1/2 of x and then worry about that 3 later on, because what the 3 is going to do is essentially stretch the y values, right? That's multiplying the outside of the function by the value of 3, so that takes a vertical stretch, which really doesn't make much of a difference on a logarithm. Not a huge difference, that is. Alright, so let's note a few properties here. One thing, I know it has a vertical asymptote. All logarithmic functions do. And since we haven't talked about any major shifts or translations yet, the vertical asymptote will be the y-axis. It will be for all these initial lectures. So it's just going to be x equals 0. So if you can imagine somebody putting a dashed line on the y-axis saying that you cannot touch this y-axis. You cannot land on it. I'm not going to allow you to. That's essentially what a vertical asymptote is. Now, we have to decide, where are we going to plot our x values? Are they to the left of the y-axis then, or are they on the other side of the y-axis? It turns out that we know the domain of a logarithmic function is all positive numbers. So I know now that it's going to be over here. I'm going to be graphing somewhere on the right-hand side of the y-axis. I know the range of a logarithmic function is all real numbers. And finally, I know that it goes through, because it's a logarithmic function, it goes to the point 1, 0. Okay, so let me go ahead and just pretend as though this point right here is 1, 0. That's what that point is. Now I have to decide. Since there's a vertical asymptote here, my graph will approach that vertical line and then curve either down or up. So I have to ask myself, is this logarithmic function, is it decreasing or increasing? This is where I look at the base. Just like for an exponential function, you always look at the base to determine if an exponential function's increasing or decreasing. Same thing for a logarithm. And actually the same rules. Since 1/2 is between 1 and 0, that means that we're decreasing. Okay, so I know that my curve should be falling, which means that it starts here and falls. Let me try to make this as nice as possible without making it look like a straight line. Okay. Then it's going to cross through 1, 0, and as it does, it's going to start really rapidly, not leveling out, but it just falls less quickly. How's that? And if you tilt your head to the right, just tilt your head to the right, you'll see that this looks like an exponential growth. If you tilt your head to the right and you imagine the x-axis is now the y-axis, you'll see that this looks like an exponential function. That's kind of because it is, in a way. So this would be the graph of 3 times log base 1/2 of x. Now often your instructor will want you to plot 2 points, if not 3, for a logarithmic function. So you have to be kind of creative with your points. One of them is pretty easy though. You should always plug in whatever the base is. F of 1/2 is equal to 3 times log base 1/2 of 1/2. Okay, wait a second. I know log base 1/2 of 1/2. That's just going to be 1. It's going to be 3 times 1, or in other words, 3. So that says when I plug in 1/2, I'm all the way at a height of 3. And then you could plug in something else. Some power of 2 probably is a good idea. So let's try f of 4. Say we're plugging in x equals 4. See, it's 3 times log base 1/2 of 4. So I need to ask myself, 1/2 to what power is going to equal 4? Remember, 1/2 is the same thing as 2 to the negative 1. So 2 to the negative 1 to what power is equal to 4, which is the same thing as 2 squared? Or in other words, 2 to the negative question mark is equal to 2 squared. Well, now I can see it. That question mark has to be a negative 2. Okay? 2 has to equal negative question mark, means that question mark equals negative 2. So therefore, when x is 4, 1, 2, or actually 1, 2, 3, 4, the y value is negative 2. Oh, no, it's not. It's negative 2, and then we're multiplying that output by 3. So it's going to be a negative 6, actually. So in reality, this should be at a height of negative 6. I didn't really draw it perfectly, obviously, but that's what it should be at. Okay, that's how you basically graph logarithms. I think what's more important with logarithms is to know how they look in general. That you know that a logarithm always looks something like either this or this. The more important one, I think, is this one right here. I use that a lot in sound processing to make a function turn up its volume slowly over time. And if you wait for my trig lectures, which might be quite some time, I do a trig lecture where I essentially turn up the volume of a sound using a logarithmic function. So it's very useful for things like that.